Hello, Chem 2. Today, what we're going to do is go over the next section of Chapter 5, talking about the different ideal gas laws. So you see what here, we've already done the green stuff, talk about the conversions. Today, we're going to try to focus on the things that are in red. So what do we got going on? Well, first off, administrative pieces. Online, there is the stoichiometry mastery exam. That is the makeup for those of you who may not have passed the first mastery. I'd like to get your grades up before they tell me that the grades have to be turned in. So if you have not yet passed the mastery, go ahead and take care of that on the OWL. There's also an aqueous stoichiometry exam. You have multiple opportunities to take care of that. Go ahead and do that. You are going to be held accountable in the long run for the content. The county is still trying to figure out what to do with that. So this is the easiest way to make sure that while things are still current and you can have some questions, you can take care of that. And then there's the two homeworks. There's the optional OWL and there's a required OWL. Again, there is going to be some accountability coming down the road, so I would take care of this while it's still fresh in your mind. Both those are for the entire chapter, so therefore you wouldn't be able to do them all after watching this video or the previous one. So let's talk about Chapter 5 and gases. We're going to focus on 2 and 3 today, a little bit about what the gas laws are and then how to use them. So the ideal gas laws, there's actually one law that's going to be covered in the next video, the ideal gas law, but these are the branches of each of those. Now, when we talked about this before, I said that there's 4 variables we're going to be comparing: pressure, temperature, volume, and number of molecules. Well, we're going to start by comparing 2 at a time while keeping the other 2 constant. So the first gas law we're going to focus on is the one that compares pressure and volume. And what it says is that if you have a closed system, which means no molecules in, no molecules out, something that is a sealed container, and it has a constant temperature, the temperature doesn't change at any time during the process. We're going to look at 2 sets of conditions, the condition number 1 and condition number 2. Same container, no molecules in, no molecules out, and then at a constant temperature. Well, what we're going to find here is that the pressure and the volume are what's called inversely proportional. Inversely means to go in opposite directions. Proportional means they're going to change the same amount. So if we increase the pressure by a factor of 2, then the volume is going to decrease by a factor of 2, again, in opposite directions. Think in terms of if you were to take a container and like a syringe or something that's filled with a gas, and you were to squeeze it, when you were to squeeze it, obviously, I think it'd become kind of common sense that the pressure inside that container would increase. So what's it look like as far as the relationship? Here's a graphical representation where you have, as the volume is very, very high, the pressure is very, very low, and once the volume is pushed down to a much lower range, then the pressure is very, very high. Mathematically, this is what that looks like. It looks like pressure times volume is going to give us K, and in chemistry, for some reason, we use the letter K for a constant. So pressure times volume is going to be a constant, but a more common way of viewing that is P times V equals P times V. You've got 2 sets of conditions. Conditions number 1, you're going to measure the pressure and the volume of a gas in a particular container at some given time. And then you're going to change things. You're going to either change the volume or change the pressure and see what happens to the other unit. This is called Boyle's law, named after a famous English chemist called Robert Boyle. So let's see this in action. So suppose you have a balloon, and the balloon has 14 liters of air. And that 14 liters of air is at a pressure of 755 millimeters of mercury. Remember from the last lesson that that's just a little bit below 1 atmosphere being 760 millimeters of mercury. A question asks, what's the volume going to be when the pressure is jacked up all the way to 151 kPa? Well, if you remember again from the last lesson, 101 kPa is 1 atmosphere. So this is actually a higher pressure than you're starting with. So the pressure is increasing. So what do you expect the volume to do? If the pressure is going to increase, hopefully you realize that the volume is going to decrease. Remember, we said they go in opposite directions. So when looking at this, we hopefully will see that we'll get a lower number. We're just going to go ahead and take all the numbers and pull them aside. First pressure is 755 millimeters of mercury. First volume was 14, so this is the first set of conditions, 14 liters at 755. Then second set of conditions is at 151 kilopascals, and we don't know what the second volume is. So we're going to plug some numbers in, but we got one problem here. The one problem is that one pressure is in millimeters of mercury and the other pressure is in kPa. So we have to convert one to the other in order to make sure they're consistent. So what I did was I took the 151 kPa and I converted it over to millimeters of mercury. So now I have both of my units are in the units of millimeters of mercury. Both my pressures are in the units of millimeters of mercury. And I'm going to take my equation, PV equals PV, Boyle's law. I'm going to solve for V2. Algebra, you're going to go ahead and divide both sides by P2. And so you get V2 is equal to P1, V1 over P2, and then just plug the numbers in. I'm going to encourage you very strongly to make sure that for long-term skills to get in this habit of writing the equation, massaging the equation or manipulating the equation in such a way to try to get to solving for the one variable that you're looking for, and then plugging in the numbers. Don't just jump into plugging in the numbers. Long-term skills can be very, very beneficial. So you go ahead and do the math. Millimeters of mercury cancels. You're left with liters. This new volume is 9.35 liters. And lo and behold, yes, as the pressure increased, the volume did decrease as we expected. That's Boyle's law. So the next law we're going to look at is the one that compares pressure and temperature. Volume and temperature. So we have volume versus temperature. What do you expect to happen? So if I were to take a balloon, and I think some of you may have done this as playing around as a kid, you might have taken a balloon, and it's weirdly enough, I don't know why you would do this, but some people do, is take that balloon and stick it in the refrigerator or the freezer. What happens to the size of that balloon? Well, hopefully, if you've ever done this, you realize, oddly enough, the balloon actually shrinks. So as the temperature goes down, the volume goes down. What that means is, in this situation, the two variables are directly proportional. As one goes down, the other one goes down. As one goes up, the other one goes up. In a closed system, again, that means no molecules in, no molecules out. And this time, the other thing we're going to keep constant is a constant pressure. There's also, if you've ever taken balloons outside in a very cold day, like say around Valentine's Day is a common time for this to happen, where you go outside with balloons. Well, those balloons will kind of shrivel and kind of become meh. They're going to get a little bit smaller, and therefore they're not going to float as high outside. That's because as the temperature went down, the volume goes down. And as the volume goes down, your density is going to get a little bit higher, and then it's going to fall and blah, blah, blah. Anyway, what's this look like mathematically? Well, if pressure times volume was inversely proportional, in this situation, we're going to go ahead and show you, this is pictures where they show you, sorry, I forgot the slide was in here, where they show you the balloons being stuffed into liquid nitrogen, getting really, really cold and getting shriveled up. And then this is right out of your textbook. Then the balloons, when they're taken out, they expand up again. Okay, so this one's called Charles's Law, named after Jacques Charles, famous French chemist. And this time, instead of being multiplied together, the product, this time the volume over the temperature is a constant. Again, we're still using that K as a constant. So the law for Charles's Law looks like this: V over 1, V1 over T1 equals V2 over T2. Again, as one goes up, the other one goes up. As one goes down, the other one goes down. You're going to see this proportionality between the two. If you double the volume, if you double the temperature, then the thing is going to expand by a factor of double. Now, one tricky part here is temperature must, like we saw in the previous lesson, must be in kelvins. So, how are we going to use this? Let's look at this example. An example of carbon dioxide. It's in a container at 300 milliliters at 10 degrees Celsius and 750 millimeters of mercury. Question is, what is the volume going to be at 30 degrees Celsius at 750 millimeters of mercury? Well, I like this problem because this was kind of tricky. Not really, but is kind of tricky. It has a trick to it. If you look at the temperatures, it appears as if the temperature went from 10 to 30. That's approximately tripling the temperature. 10 times 3 is 30, so you see a tripling of temperature. So you would anticipate that the volume would change by a factor of 3 also. However, here's the tricky part. Both these temperatures are in degrees Celsius. Charles's law works only, and all the gas laws only work in kelvins. So we have to convert our units over into kelvins. So our initial volume is 300 milliliters. Our initial temperature is 10 degrees Celsius. And our initial volume is, I don't know. Our second volume is, I don't know. And our second temperature is 30. We have to convert both of them over to, both temperatures over to kelvins. And you'll see now there's a much less significant increase in our temperature. So I hope to see a much less significant increase in our volume. But it still should go up. So Charles's law is V over T. We have to solve for V2, which is right here. You do that by multiplying both sides by T2 to get rid of the T2. So V1 times T2 over T1. And when you plug the numbers in, you get a volume of 321 milliliters. And again, slight increase, but definitely an increase. So Charles's law, volume and temperature are directly proportional. Volume and temperature are directly proportional. Third law that still maintains keeping the number of molecules constant is called the P over T law, or sorry, the PT law. You have pressure and temperature. Again, let's think about it. Anybody who's ever been crazy enough to take been at a campfire and been very bad. I know some of you guys have done this, usually people with Y chromosomes, where you'll take a aerosol can and put it in a fire. What's it do? Now, some of you are like, why would anybody do that? Well, just being boys will be boys, tends to explode. The reason for that is you increase the temperature, the pressure inside the can expands dramatically. And when it does that, you're going to get an increase in pressure. So how are these related? Well, if you increase the temperature, the pressure increases. These are also going to be directly proportional, just like Charles's law. In a closed system, meaning the can is sealed. We're not going to let any molecules in, no molecules out. And we keep the size of the container constant, at least until it explodes. So the size of the containers, it's a very rigid container. It does no molecules in, no molecules out. The temperature and the pressure will be directly proportional. This was called Gay-Lussac's law. Gay-Lussac, named as Jacques Gay-Lussac. Gay-Lussac's law is pressure over temperature is a constant. Looks a lot like Charles's law, where you're going to be solving for, again, pressure, long as they're the same on both sides. Like we saw with Boyle's law, we had to make sure the pressures were the same on both sides, the units were the same on both sides, and temperatures must be in kelvins. Have to not only be the same on both sides, but need to be in kelvins. So let's look at an example. Suppose we have hydrogen occupying a volume of 250 milliliters at 10 degrees Celsius and 750 millimeters mercury. What is the temperature going to be if we want to make sure that the pressure gets to 1.5 atmosphere and making sure the volume doesn't change? The volume doesn't change at all. All that's telling me is that I want to make sure that I can use Gay-Lussac's law because volume doesn't change and no molecules in, no molecules out. So my initial pressure, 750. My initial volume, 250. My initial temperature, 10 degrees Celsius. My new pressure is 1.5 atmospheres. Volume 2, it says no change, so it's going to be the 250 millimeters of mercury, 250 milliliters. And then my new temperature is what I'm going to solve for. So how are we going to do this? First off, we have to change our temperature to kelvins. We cannot use Celsius, must use Kelvin, must use kelvins. Second thing is, you'll notice that my pressures are in two different units. I need to change one over to the other. So I'm going to go ahead and take my 1.5 atmospheres and convert it over to millimeters of mercury. But I'm going to make a note to myself that 1.5 is only two significant digits. So I'm going to go ahead and express my answer possibly to two significant digits. So look at my Gay-Lussac's law. Pressure over temperature equals pressure over temperature. I'm going to go ahead and solve for T2. The way I would do that is cross multiply and then divide both sides by P1. I get T2 equals P2 times T1 over P1. Plug the numbers in, get an answer. That means my new temperature has to be 430 kelvins compared to 283 kelvins. that's a pretty big increase in temperature, 160 degrees as opposed to the 10 degrees we started off with. So how do we put this all together? Well, we have three laws. We have the Boyle's law, pressure times volume is a constant. We have Charles's law, volume over temperature is a constant. And we have Gay-Lussac's law, pressure over temperature is a constant. Notice the pressure and the volume are always in the numerator and the temperature is in the denominator. So if we put it all together, we get what's called the combined gas law. Pressure times volume over temperature is a constant. What's the benefit of this? This allows us to change three variables at the same time: the pressure, the volume, and the number of molecules. Sorry, say that again. This allows us to change three: pressure, volume, and the temperature, while maintaining only one thing being constant, that is the number of molecules needs to be constant. No molecules in, no molecules out. This is a closed container, but works for all three at the same time. Let's look at how this might function. Now let's look at this going crazy. We have a gas at 253 liters at 1.5 atmospheres and 85 degrees Celsius. I want to know what's the Celsius temperature. Darn, let's make this crazy. Celsius temperature. If the gas occupies 151 liters, it's getting smaller and has a pressure of 75 kilopascals, which it's getting smaller. So the pressure is getting smaller and the volume is getting smaller. So let's see what would happen to the temperature. So our pressure 1 is 1.5 atmosphere, volume 1 is 253. Temperature 1 is 85 degrees Celsius, pressure 2, volume 2, and then I need to solve that, and I need to make a note to myself that I need to change it back to Celsius. So change my atmospheres over this time to get to kPa. I don't know why, but I choose to do that. And then change my temperature over to Kelvin, so I can put these numbers into the combined gas law. So there's my variables as I know them, and again, this kPa, this has only 2 sig figs, but I have it written out completely so I can use the whole thing. But here's my combined gas law, and I solve for T2, again, by cross multiplying P1 V1 T2 equals T1 P2 V2, and then dividing both sides by P1 and V1, I get this expression for what T2 is. Plug all the numbers in, and I get that I am at 110 kelvins, only 2 sig figs, which is a negative 160 degrees Celsius. In order for my pressure to go down that much and my volume to go down by that much, my temperature has to dramatically decrease from 358 down to 110, or from that 85 down to negative 160. Crazy, crazy, crazy drop in temperature. Okay. So what's next? What we're going to do in our next video is we're going to focus on how to bring some of these pieces together, and maybe we're also going to incorporate how to snag out and incorporate the last variable, the number of molecules. Hopefully this has been helpful. You should be able to do a little bit more of the OWL now. Starting next week, there's going to be a lot more consistent output of these videos, maybe smaller and shorter, but it's going to be definitely a lot more consistent. We've been told to try to give you guys the opportunity to continue your studies. So in the event that some of you guys do come to AP Chem, that you're ready for the next level. So anyway, hopefully everybody is staying safe, is looking forward to a very, very interesting next 4 weeks of school. I hope that everybody does take care of themselves and stay safe, stay clean, wash your hands, practice that social distancing, which means I know you guys are all going stir crazy, not being around one another. But I'm really missing you guys, and hopefully in another 4 weeks, we can get back to some degree of normalcy. And always remember and never forget, you know it, sig figs do matter. See you later. Bye.